All right, now that we've reviewed inverse functions, now I want to talk about this theorem that's going to tell us how we can actually differentiate inverse functions. So our theorem is just the derivative of an inverse function, and it starts out by saying, suppose that we have some function, call it g of x, and it is equivalent to f inverse of x. The reason why we're going to do it this way is because it looks nicer, and then I'll switch it over to looking at, well, what about if it's f inverse of x instead of g of x? So g of x is our inverse, and it's the inverse of some original function f of x. As long as my original function was differentiable, then g is differentiable as well. So my inverse is also differentiable as long as f prime of the inverse does not equal 0, which shouldn't be a problem because f prime of my inverse should just give me x back. So notice that I cannot do it if x is 0. So that being said, my inverse says derivative is g prime of x equals 1 over f prime of x. So another way to see this written is to say if g prime is f prime, if g prime is the derivative of g and g is f inverse, then g prime is just f inverse prime of x. So the derivative of my inverse of x is equal to 1 over f prime, my original function, of f inverse of x. It is also sometimes known as the derivative of y with respect to x is equal to 1 over the derivative of x with respect to y. And then looking at some examples where we use this. So suppose I'm told in example 1 that f of x is this function here, is this function here, 0.25x cubed plus x minus 1, and I need to find f inverse prime of x when x is 3. Well, the formula for that, remember, so the derivative of the inverse when x equals 3 will be equal to 1 over f prime of f inverse of 3. So basically I need to know two things in order to figure out this function. I need to figure out what is f inverse of 3, and then I'm going to have to find the derivative of my original function so that I can solve this. So if you watched on the last slide when I reviewed some inverse functions, or on the last video when I reviewed inverse functions, I had two ways to figure out what is f inverse of 3. One way I could do it is to say, well, what if f of x equals y? Then y equals 0.25x cubed plus x minus 1. Switching x and y, I get 0.25y cubed plus y minus 1. So if I tried to solve this for y, I could add the 1 to both sides, and I could try factoring out of y. But what you'll notice is when I try doing that, I'm still going to have y squared inside of my parentheses, and it's going to be really hard to get y by itself. If you don't believe me, please try. So I'm going to look at the other way we looked at. So I'm going to go ahead and switch gears and say, you know what, I don't like this. I'm going to struggle to get y by itself. I can see that already. And I'm going to say instead that I know if f of x has the point a comma b, then f inverse of x has the point b comma a. And I want to figure out what is f inverse when x is 3. So when x is 3, what is the y value of my inverse? Well, that means that when f has an x value of a, it has a y value of 3. So I can go ahead and take this 0.25x cubed plus x minus 1 and ask myself, when does it equal 3? Using the solver function on my calculator, I find out that x equals 2. We will go over this more in depth in class tomorrow, how to use your calculator to get that answer. Okay, so now that I know that f inverse of 3 equals 2, I can go ahead and plug that in here. I can also see that I'm going to have to be able to find the derivative of my original function, so I'm also going to go ahead and differentiate that. So differentiating that, if f of x equals 0.25x cubed plus x minus 1, then f inverse of x equals 3 times 0.25. I know 0.25 is the same thing as 1/4, so I get 3/4 x squared plus 1. So now that I have all my information I need, I'm going to go ahead and I'm going to plug into my original function. And I'm going to say that f inverse prime of 3 equals 1 over f prime of f inverse of 3, which I found to be 2, which gives me 1 over, when I plug 2 into my first derivative, I end up with 2 squared is 4, so my 4's will cancel out. So 3 times 1 plus 1, so I get 4. And so there would be the derivative or the slope of my derivative when x equals 3. So at the point 3 comma 2, because remember I solved for that a right here, at the point 3 comma 2, I found that my inverse function had a derivative of 1 over 4. Notice that I didn't write it out, but I also found out that at the point 2 comma 3, my original function had an inverse of 4. So notice that my function and its inverse have reciprocal slopes at the point a comma b and b comma a. Looking at the next example, what if, same thing, I now know that f of x is the square root of 2x minus 3. Can I find f inverse, the first derivative of f inverse of 5? So writing down my formula, f inverse prime of 5 equals 1 over f prime of f inverse of 5. So again, I have to, in order to evaluate this function, I have to find two different things. I have to find f inverse of 5, and then I also have to find f prime. So I'm going to go ahead and find f inverse of 5, knowing that if f of x has the point a comma b, then f inverse of x has the point b comma a. So if I know f inverse of x, or if I'm trying to find f inverse of x when x is 5, I know that my original function had that same y value when its y value, or had that same x value when its y value was 5. So I'm going to go ahead and say, okay, I can set my original function 2x minus 3 equal to 5 and say what x value made my original function have a y value of 5, because that x value will be the y value that corresponds with 5 for my inverse. So solving this, I can square it and say 25 minus 3, or excuse me, 2x minus 3 equals 25. 2x equals 28, and therefore x equals 14. So up here, then when does my inverse, or what is the y value when my inverse is, when I plug 5 into my inverse function, my y value is 14. So I now have this piece, but I'm also going to have to know my f prime of my original function. So I'm going to go ahead and differentiate this as well. So f prime of x equals, well, I notice that I have a composite function here. I have 2x minus 3 as my inside function, and the square root function as my outside function. So I'm going to do a little bit of work here and say my inside function is 2x minus 3. My outside function is u to the 1/2. So u prime is 2 and v prime is 1/2 u to the negative 1/2. And so when I do u prime times v prime, 2 times 1/2, they cancel out, and I get u to the negative 1/2, which is the same thing as 1 over u to the positive 1/2. And remember, so I didn't write out very well, so sorry, I will, so let me read it so you can get that written down a little bit better. It is 1 over 2x minus 3 in parentheses to the 1/2 power. So now I'm going to go ahead and I'm going to plug back into my formula, and I'm going to say f inverse prime of 5. So the derivative when f inverse of 5 equals 1 over f prime of f inverse of 5 was 14, which equals 1 over f inverse of 14. So plugging 14 into, excuse me, f prime, plugging 14 into f prime, I am going to go ahead and write that 1/2 as a radical, just an FYI. 1 over the square root of 2 times 14, which is 28 minus 3, which is 1 over the square root of 25, which is 1 over 1/5. Well, dividing by 1/5 is the same thing as multiplying by 5 over 1, and 1 times 5 over 1 is 5. So at the point 5, 14, my inverse function has a derivative of 5, or a slope of 5. Well, notice that if my inverse contains the point 5, 14, then my original function contains the point 14, 5. So my inverse function at the point 5, 14 has a derivative of 5. My original function at the point 14, 5 has a slope of 1/5. So once again, notice that my inverse and my function have reciprocal slopes at the point AB and BA. So one last thing to talk about then. So this is kind of what I've been trying to point out all along as we went over those last two examples, is that f of x and f inverse of x have reciprocal slopes at the point AB and BA. So suppose on this last example I knew that f prime of x equals 6 at the point 3, 9. So the slope of my original function at the point 3, 9 is 6. Can I determine from that information alone what the slope of my inverse function is at the point 9, 3? Well, yeah, all I have to do is say it's the reciprocal of the slope of my original function. So if the derivative was 6 at 3, 9, then the derivative of the inverse at 9, 3 is 1 over 6.